So in this lecture, we're going to continue our study of modular arithmetic. And in particular, we would like to know when we can do division in the integers modulo m. It turns out to be a bit tricky. But first I'd like to just start by reviewing what our object of study is. So last time we looked at the integers modulo m. M can be any natural number. So for example, we can look at the integers modulo 6, which we call z mod 6z. That's the modern notation for it. And this ring, z mod 6z, it has 6 elements. There's 0, 1, 2, 3, 4, and 5. And the element 6 belongs to the same congruence class as 0. If we only can put bars over to use to sort of denote they're special. 6 belongs to the same congruence class as 0. All multiples of 6 belong to this same class, including the negative multiples. And for example, in this class, the class of 2, we have anything in the form 6n plus 2. So we can go up and down by multiples of 6. So we have 8, we have 14, we have 20, etc. In this class we have 11, 17. We can go the other way too, negative 1. And we introduce this notation of congruence. So we say A is congruent to B mod m. Here m is 6. This just means nothing other than A and B differ by a multiple of m. So A minus B is some multiple of m. Okay. Well, what are some examples? So we can say actually, 2 is congruent to 8 mod 6. And we can do arithmetic. So for example, 2 plus 4 is congruent to 0 mod 6. 2 times 4 is congruent to, this is 8, but if we want, instead of 8, we can write 2. Could have written 14 or 20 as well. So it's also mod 6. And we developed a few properties, so let's just recall those. So we can basically add, subtract, or multiply congruence equations. So we can add, subtract, or multiply congruences by the same number. And by the same number, I even mean you can use congruent numbers. So it doesn't have to be the same integer even. It can be congruent numbers. What do I mean specifically? So, for example, last time we proved a couple of statements like this. So if we want to do maybe a plus b, but if a is congruent to something else, and b is congruent to something else, mod m, then if I do a plus b, I could also do c plus d. I could replace a and b with congruent numbers, and we get the same thing, mod m. And this is true for subtraction. Additive inverses always exist. This is also true for multiplication. This is a little bit trickier to prove, but a times b is going to be the same as c times d. If we replace a and b with congruent numbers, mod m. It's all mod m. Okay. You notice something's missing here, though. So what about division? What about division? And so already we should be a bit skeptical here. So, for example, let's just look at this equation here. So 2 times 4 is congruent to 2 mod 6. What if we divided this by 2? Well, we get 4 is congruent to 1 mod 6? Question mark. Which is put a question mark because that's clearly not true, right? 1 and 4 are different congruence classes, so this is not true. So we're not allowed to just divide by the 2 here. However, division is actually possible more than you might think, more often than you might think. And that's what we want to study today. So sort of exactly when can you divide and how do you do it? And this is actually a bit subtle. So I'd like to do some examples first to illustrate the possible things that could happen. So here's some examples. And I'd like to actually do some examples from sort of some real life situations maybe that you've thought about before. So let's look at the integers modulo 12. So I'm going to think about this as time on a clock. So let me set up a situation maybe where we want to divide some amount of time. So suppose I do 2 consecutive tasks, one after the other, and each is the same number of hours. Is the same. Let's say that each task is a whole number of hours, so there are no fractions of hours. So the same whole number of hours. And let's say the first task starts at 6 o'clock. Just on a clock. I'm not saying whether it's 6 in the morning, 6 in the evening. It's just 6 o'clock on the. That's all I can see. Look at the clock. It says 6 o'clock. The second. Let's say the second. We know when both tasks end. So the second task ends at let's say 10 o'clock. And what do I want to know? I want to know how long is each task. We know they're both the same length, but can we figure it out based on this information? So you might say, well, wait, what if I start at 6 o'clock today and I end at 10 o'clock a month from now? So this is not really going to be well defined. Like I can't really say how long is each task. So let's say instead I want to say how long is each task modulo 12. Okay, so as we can differ, like for example, well, I mean, I'm sure you're already thinking what the answer is. So there's an obvious answer, right? Obvious answer. The obvious answer is that the first task ends at 8, so we go 6 to 8. Draw a little clock, actually. Draw a few little clocks here. So we start at 6 o'clock. Looks like that. And then we go to 8 o'clock for the first task. And then we go to 10 o'clock for the second task. Okay. So each task is 2 hours. Modulo 12. 6 o'clock, 8 o'clock, 10 o'clock. Obvious answer, 2 hours. So I should be clear. So what if we go from 6 o'clock today to 8 o'clock tomorrow? Well, that actually differs by. So it would still be 2 hours modulo 12, but if you calculate it out, it would actually be 26 hours. But that's so there's definitely some ambiguity here. But modulo 12, we can say, it's going to be 2 hours. However, things are a little bit more subtle than they seem. So there's another answer. So that's the obvious answer, but there's another one. Modulo 12 even. Can you think of what it is? There's another answer. And draw the clocks again. So my starting time is 6. My ending time is 10. What if we go 6 o'clock, 7 o'clock, 8 o'clock, 9 o'clock, 10 o'clock. We pass 10 o'clock. We go around to, what would it be? 2 o'clock, I think. So we go from 6 o'clock to 2 o'clock. And then we go to 10 o'clock. So each task will be 8 hours. Okay, so there's another answer, which is 8 hours. That's a different answer modulo 12 even. Right? 2 and 8 are not even equivalent modulo 12. So we get two possible answers. Which is a little bit strange. Let's investigate this a little bit further. So let's say x is the length of the task. X is the length of the task. It can be in the integers. We're about to look at an equation modulo 12 though. So what is the equation that we want to solve? We want to solve, well, we know modulo 12, 4 hours have passed. So we want to solve 2x equals 4 modulo 12. So 2x is congruent to 4 modulo 12. And somehow this congruence, so it seems like we can divide by 2 and get x equals 2, but somehow this congruence has a solution 8 as well. So what's going on here? Well, here's my advice. So whenever you're confused, like whether you can or can't do something in a congruence, what I would do is write out the definition, write out this definition, turn it into a problem in the integers. This is a problem in the integers, just a normal equal sign. So what do I mean by that? So we want to solve 2x and 4 differ by a multiple of 12. 2x minus 4 is 12, Now we see maybe what's going on, because everything in this equation, like there's an obvious algebra step to do here. You can just divide by the 2. Divide that whole equation by 2. So divide by 2. We get x minus 2 is 6k. What does that say? That says x is congruent to 2 mod 6 even. Not 12, but mod 6. That's more specific than mod 12. And we see if we do this, we get our solution of 8 as well, because x can be 2 hours, it can be 8 hours, it can be 14 hours, it can be any of these things here. So we actually get a solution to this incongruence mod 6. So it seems like what we did to go from here to here, and this is something that we can do in general, if everything here, this one, that one, and the modulus, have a common factor, we can divide through by that factor. But we have to divide the modulus also, or else we might lose one of our solutions. Okay. So that's the first weird thing that can happen already, but there's more. So let's look at another example. Let's do the same setup. So this will be a fairly quick example. So same setup, but the first task starts at 6 o'clock, and the second ends at 9 o'clock. Instead of 10 o'clock, ends at 9 o'clock. And so we don't have a solution like this anymore, because each task has to be a whole number of hours. So we can't go 6 to 7:30 to 9. Each task is a whole number of hours. And if you think about this, even if you try to sort of wrap around like we did here, this is just not going to be possible. And the reason for that is now we want to solve 2x. So whatever our task length is, 2 of it is going to be 3 hours. So 2x congruent to 3 mod 12. Well, what happens if we just turn this into, use the definition to get a statement in the integers? So 2x and 3 differ by a multiple of 12. And this is just not possible. So one way to see that, let's move to 12k over, put the 3 on this side. Let me see. This 2 divides this term. 2 divides this term. That would imply that 2 divides 3. That's a contradiction. So there's just no possible integer values of x and k that satisfy this. So there's no solution. So we cannot divide this one by 2. It just doesn't work. We don't get any solutions. Let's look at a slightly different situation, but very similar. So example 3, I guess. I think I want to do 4 examples total, because it's good to get a feel for what kinds of things are happening here. before we look at a specific statement. So let's now suppose let's do longer tasks. So let's suppose I take 2 consecutive trips. Each the same whole number of days. So same setup as before. Except we're doing days, not hours. Each the same whole number of days. And let's say I leave on Monday. And I return. So leave for the first trip on Monday. And I return from the second trip on a Friday. That's all I know. So this is a problem about the integers modulo 7, right? Because we have 7 days. So Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. So this is a problem modulo 7. I leave Monday, I return Friday, and I want to know the same thing. So how long is each trip? All right. What do we want to solve? If x is the trip length, so let's say x is the trip length. Just of one of the trips. And we want to solve 2x is congruent to 4, right? Because 4 days have passed for both of the trips. This time it's modulo 7 instead of modulo 12. Well, can we do the same thing as before? Again, you might see, oh wait, there's an obvious answer, right? So Monday to Friday, Wednesday is going to be the halfway point, so it's going to be 2 days. But what do we do before? We saw we could divide this whole congruence by 2. However, if we didn't divide the modulus by 2, we missed out on a solution. So what about this one? We can't divide a 7 by 2, right, in the integers. That doesn't make any sense. So, again, if you're ever unsure about what to do, use the definition. Change this to a statement about integers. What does congruent modulo 7 means? It means 2x and 4 differ by a multiple of 7. Now we want to know, does this have a solution? So maybe what I'll do is I'll move this 7k over, and I'll move the 4 onto that side. So does this have a solution? Is there an x and a k? Like I can choose k to be whatever I want. So is there an x and a k, integers, that make this statement true? Does this have a solution? Well, this looks familiar. So if you've seen a lecture on the Euclidean algorithm, let's just recall something. So recall, if we have 2 integers, so if a and b are 2 integers, so that the GCD of a and b sorry, let me write this out a little differently. So if a and b are integers with GCD, let's call it d. So d is the GCD of a and b. Well, we can do something very interesting. Then we can write that GCD as a linear combination of a and b. So we can write d is ax plus by. We can find some x and y in the integers. Okay, so we can actually write d as a linear combination of a and b. This looks very similar to that, right? The same setup. So here my a would be 2, my b would be 7. We can put a negative sign inside the k if we want, it doesn't really matter. And the GCD of 2 and 7 is 1. So note, GCD of 2 and 7, so note, GCD of 2 and 7 is 1. So we can even write 1 as a linear combination we can find this x and k. So we can even write 1 as a linear combination of the 2 and 7. We want to know, can we write 4 as a linear combination? Well, sure, yeah. So how do we do that? We talked about this before. You just multiply this equation by 4. So just multiply, you can say multiply the x and the k by 4. And you get a solution too. So this x is 4 times the other x. Sorry, it's a little bit confusing. Call it x bar, k bar. This is whatever 4 times the x, 4 times the k is. Yeah, so we can get a solution to this equation easily because 4 is a multiple of the GCD. Okay. What is that solution? Just to show us in a little more detail. So what is the solution? How do we write 1 as a linear combination? Well, the way we did that is with the Euclidean algorithm. But I wouldn't use the Euclidean algorithm here. It's easy enough to see that if we did 2 times 4 minus 7 times 1, we can write 1 in that way. So here, this is my x, and this is my k. And now if we just multiply this equation by 4, I'll show you exactly what I mean. So 2 times 16 minus 7 times 4 is 4. So we've now found a solution to this one. So there's my x, there's my k. What do we really care about? We care about the trip length. We care about the x. This is a solution. This is the solution to my original. I don't even care about the k really in this case. This is my solution to the original congruence. So this is a solution to 2x is congruent to 4 mod 7. You can say, well, 16, that's not, we can make 16 smaller, right? So 16, we can, what congruence class is that? It's 2 more than 14. It's 2 more than a multiple of 7. So x is congruent to 2 mod 7. Okay. This is a lot of work to kind of show that somehow you can divide here. However, I don't want you to get the wrong idea about this, so I immediately want to change the problem slightly. This will be the last example, I promise. So same setup as the previous one, but let's say I leave on Monday still, but I return 1 day earlier. I return Thursday. Is that possible? Well, with the clock, it was not possible, right? It was not possible to solve 2x congruent to 3. That's the same congruence here, right? We want to solve 2x is congruent to 3, but this time modulo 7. Can we solve this congruence? Well, first glance, it seems maybe no, we can't. But there's actually a way to do it. And, well, here's how you can think of it. So if we go back up here, we want to leave on Monday and return Thursday. Okay, but this is a length of 3. But what if we return next Thursday? That would be 10 days. Right? And 10 is divisible by 2. So we can do a 5-day trip. We return Saturday morning, and then we leave for our second trip. Okay, so our second trip is going to go into the next week, and then we'll get back Thursday morning. So this is possible. We can apparently take a 5-day trip. And that's the only solution if you think about it for a while. Well, how can we see this mathematically? Because here, certainly we shouldn't be able to divide by 2, because 3 divided by 2 doesn't really make sense. It turns out we still kind of can. So let's do the same thing as before. So we'll turn this into a statement in the integers. 2x minus 3 something I really want you to get used to doing. So that's equivalent to the statement in the integers. And if we rearrange things, this again looks like this equation here. So we can even write 1 as a linear combination of this. So we can write 1 as 2x minus 7k equals 1. We did that. 2 times 4 minus 7 times 1. So certainly we can write 3 as a linear combination of these two. We just multiply the x and the k by 3, just like we did before. Just write that out explicitly. So multiply by 3 this time. And again, this works because, if we can write 1 as a linear combination, you can write any number as a linear combination of these two. Right? Because every number is a multiple of 1. So this is how I do it. Thus I'm keeping the 2 and the 7 the same. I'm choosing to multiply these ones by the 3. I have to choose to multiply something by the 3 in each term. So which one was my x? Wait a second. This one, yeah. The 12 was my x. So this is my x. And this x is a solution to the original congruence. So we get x is congruent to 12, or 5. That's an even better way to write it. Modulo 7. So this example shows, even if it doesn't look like you can divide by the 2, you still can. But we have to make it clear what we exactly mean by division. And so in general, I would say division is not really a thing in congruences. But still, you can basically do something that's the equivalent of division in order to solve a congruence. And we did that basically through this process, converting it to an equation in the integers, and then using this very important statement. Let me box this. So we can write the GCD of two numbers as a linear combination of the two numbers. And that's a very important fact that we're using here to solve these congruences. Okay, so let's try to do a general statement now. So, in general, I think those examples basically show all the weird things that can happen. So, in general, to solve this kind of problem, ax is congruent to b. This is a linear congruence. That's what the title of the lecture is referring to. And all you really want to do is divide by a, but that's as we've seen. Sometimes it looks like you can and you can't. Sometimes it looks like you can't and you actually can. Sometimes it looks like you can, but you can actually get more than one solution. So we have to be very careful about this. But to solve this kind of equation, first use a definition of congruence. Definition. What do I mean? Ax minus b is a multiple of m. Easy enough. So let me write mk. Let's put the variables second. So m is some fixed thing. K and x are the variables. So I want to solve this. And to solve this, we make it look like this. So we have some linear combination of a and m, not a and b, but a and m. We need a linear combination of a and m to get b. And when is this solvable? So this is solvable. We can find x and k. And again, we don't really care about what k is. Like, we're really going after x. But it doesn't matter. I mean, you kind of get them both for free. But yeah, when can we actually solve this? So this is solvable if b is a multiple. It doesn't have to be exactly the GCD of a and m. It only has to be a multiple, because if it's a multiple, we can take a linear expression for the GCD and just multiply it by whatever we need to get B. So it's only solvable if B is a... sorry, let me write this a little clearer. It's only solvable if B is a multiple of the GCD of A and M. Okay. That's the condition. What if B is not a multiple of this? Well, then we have a problem. Then it's like this situation. Where we... is it like this situation? Yes. So here we had two numbers, and 3 was not a multiple of the GCD of these two numbers, which was 2. So these numbers share a factor that that one does not have. That's a contradiction. So we really need it to be a multiple of the GCD of A and M in order to have a solution. Otherwise, there's no solution. Because A and B would have this as one of their multiples. That implies B has to have that as well. So if it doesn't, there's definitely no solution. So it's actually if and only if. And only if B is multiple of GCD of A and M. How do we find that solution? Well, what we do is we would first solve. So let me call D the GCD of A and M here. So we first solve AX minus MY equals D, the GCD, using Euclid's algorithm, using the Euclidean algorithm. We'll do an example of this, just to remind you how to solve this, using the Euclidean algorithm. We first solve that, but we want a solution to this, but if B is a multiple, so I'll say if so, right, D to be the GCD, and we first solve this equation, and then if, we know B is a multiple, so then we multiply this equation. And what exactly do I mean by multiply the equation? I specifically want to, sorry, I should put a k in there instead of a y. I want to multiply x, k, and d by, what number is it exactly? I guess it's b over d. B over d. Sorry, I'm getting a little lost in the variables, so I think we'll switch to an example really soon to get a solution to our original one. Mk equals d. Sorry, b. And then this x will be the desired solution to our congruence. Ax is congruent to b. So we're really using a lot of things that we've built up so far in this class. This turns out to be a problem involving GCDs and the Euclidean algorithm, surprisingly enough. I should say not the desired solution. It could be a desired solution, because we remember what happened in our clock example, our first clock example. We actually had two solutions crop up. We had a 2 modulo 12 or 8 modulo 12. And that's because it turned out we actually could divide this whole thing by 2. This statement, if you're ever confused if you can do something, just switch it to a statement in integers. It's clear we can divide this equation. It's an equation of integers. We can definitely divide this by 2. And we actually get solutions. We get a solution mod 6, so we get 2 different solutions mod 12. And I could say, yeah, in general, there will be, there will actually be several different solutions. So how many exactly? Well, we're dividing, in that case the GCD was 2. So we divided by 2. Our modulus actually shrunk by a factor of 2. In general, our modulus is going to shrink by a factor of d. So in general, there will be d inequivalent solutions. Modulo our original m, or there'll be one solution modulo whatever the smaller modulus is, m over, we can divide m by d. Okay. Let's look at an example. I think this is already getting a bit confusing with all the letters, so I want to do an example where we actually do get a bunch of inequivalent solutions. So I'll show you how to actually deal with those. So let's solve the congruence 21x is congruent to 15. Looks a bit strange, but this is going to be possible. Mod 36. It's not going to be possible with every modulus, so there's a very specific condition that we're going to have to check. So we want to solve this this congruence modulo 36. Of course, one way to solve this is just try every value of x from 0 up to 35 and see if you get something that works. Let's see if we can do it more efficiently. So what do? I'm looking at this, so I'm a bit confused, so I'm immediately going to turn it into a problem in the integers by using the definition of congruence. That's the definition of congruence. These are congruent modulo 36 if they differ by a multiple of 36 in the integers. So this is an equation in Z. Okay. Well, all we're really solving in disguise is this equation, which is essentially Euclid's algorithm. Or Euclid's algorithm is a tool we use to solve this kind of thing. But let's check to see if it's even solvable. In fact, these numbers aren't that big, so I can pretty much figure out what the GCD of the 21 and the 36 is. These are numbers we want to take the GCD of, right? It's actually that and that. It's these two numbers in a linear combination. Let's use Euclid's method anyway. So we want to do the GCD of 21 and 36. And the reason I want to use Euclid's method anyway is because I'm eventually going to, if it is solvable, I'm going to need to write the GCD as a linear combination in order to actually get a handle on the solution. So let's find this GCD with Euclid's algorithm. So 36 is, I'm going to go through this relatively quickly, but there's a whole lecture on Euclid's algorithm if you want to see all the details. Plus 15. Now I take these ones, 21 and 15. So 21 is 1 times 15 plus the remainder 6. And then I take these two. 15 is 2 6s plus the remainder of 3. And 6 is just 2 3s. So there's no remainder. This one right here is my GCD. Okay, that's my GCD of 21 and 36. And notice that 15, so 15 is a multiple. So 15 is a multiple of the GCD. So it's solvable. This is the GCD. So it's solvable. And because we have a GCD of 3, we're actually going to get multiple solutions. We'll get 3 solutions, in fact, modulo 36. Let's start out by just trying to find one. So how do I do that? Well, I actually need to solve this statement here. And this is, if you remember, this is where we basically imitate these steps, but we do it symbolically. So I'm going to call this A, and I'm going to call this B. And I'm just going to copy down the same thing. So A is 1B plus, how do I get that 15? I need to write it in terms of A and B. So that was just the remainder, 36 minus this. So this A minus B. And then what happens in my next step, I take B and A minus B. And B is 1 times A minus B plus whatever's left over. What's left over? It's b minus this, so that'd be actually 2b minus a. That's my remainder. Okay, now I take these two. So a minus b is 2. So you do need to have gone through this because I need to see what my my quotient is here. So it goes in 2 times. So it's 2 times this one, the previous remainder, plus what's left. That'll be my GCD. So it's just gonna be this minus that. What is that? It's a minus negative 2a. So it's 3a, and it's minus b minus 4b. So minus 5b. So this is my GCD. This is my GCD. That's equal to 3, right? My GCD of 3. What are a and b? A is 36 and b is 21. So we have just written 3 as a linear combination of 36 and 21. What is that linear combination exactly? So it's this. So 3 times 36 minus 5 times 21 equals 3, right? My GCD. We didn't want to solve that. We wanted to solve this one. So we need to multiply everything by 5 to get to 15. So I need to do times 5. And what am I going to end up with? So what am I multiplying by 5 exactly? Well, these I don't want to change. Remember our goal. Our goal is to solve this one. So I'm going to keep the 36. I'm going to keep the 21. I'm just going to multiply these things by 5. So what do I get? I get 15 is some combination of the 36 and the 21 still. But this is now 25. And this one is now 15. Okay, so my answer is probably here staring me in the face. Let's try to find it though. So what is my answer? My answer is going to be the x. I want to find the x. Well, this is whatever my coefficient of the 21 is. So 21x, not negative 21x. So this is my x apparently. That's my x. So I can take x to be negative 25. X equals negative 25 is a solution. Well, what's negative 25 modulo 36? That's 11. Great. So we found a solution. And I say a solution. That's not the only one. What do I mean that's not the only one? There are more solutions. And the reason is, so there are more solutions. There are more solutions. The reason is, so be D in equivalent solutions, GCD, number, whatever GCD is. Why is that? Now we're going to see how you actually get those solutions. So let's take our equation here in integers. We have a solution to this, which is negative 25. What if we just divide this by the GCD? Because after all of these things, all of these numbers have a GCD as a factor. So let's divide by the GCD. What do we get? We get 7x, GCD is 3, that's 12k, equals 5. So we actually get a solution to this. Okay, we get a solution to this equation, which in modular arithmetic is actually, if we kind of convert it back, so I'll move the 5 over, put the 12k on that side. This is actually saying 7x, we can choose k however we want, but 7x is congruent to 5 modulo 12. Okay. Notice how the modulus changed here. The modulus is now 12. And so this one is a solution to this, but any solution to this equation in the integers is also going to be a solution to this congruence, just because this is totally equivalent. See, over the integers, this is exactly the same as this, right? Let me draw, yeah, these two things are equivalent. Okay. So actually, I get a solution modulo 12, not 36. But this, I can just take my same solution. So x is congruent to 11 mod 12. I want a solution modulo 36. I can take 11 if I want. I can also take 23. I can add a multiple of 12. Or I can add another multiple of 12. And I get 3 non-equivalent solutions. Mod 36. These are not equivalent, but they're all solutions to my original congruence. Okay. If we only care about one solution, we can just stop here, though. But yeah, in general, you should be aware that there are some other solutions that can come up. And the number of solutions is whatever this GCD is. Essentially, the way you get them is you can actually just divide this modulus as well by the GCD. And so you actually get a solution, not only 11 mod 36, but 11 mod 12, which actually gives me 3 different solutions mod 36. So this is not all the solutions. This is only one solution. So this is one possible solution. But this is how I would start. Yeah, try to just find one solution, and then it turns out you can divide this entire thing by the GCD to actually get a mod 12 statement instead of a mod 36 statement. Okay, so I'd like to introduce one more concept today. So this is going to be the concept of a modular inverse. So we've seen that division is very complicated. It's not really a thing. You shouldn't really think that you can divide. Sometimes you can do something equivalent. However, there are actually some numbers you can always divide by. So there are some elements. It's never going to run into tricky situations. There's some elements of z mod nz. They're called units that you can always divide by. Okay. Before I tell you exactly what those elements are, let's think about if division is not a thing, and then what exactly do we mean by division? So, or divide by. So the idea is, let's say we have a division problem in the integers, or let's say the rational numbers even. So a and b are integers. Well, what does it mean? This really means you do a times the reciprocal of b, or in other words, the multiplicative inverse of b. So this is the multiplicative inverse of b. And this is why you can't do division in the integers. You need to go to the rational numbers, because you might end up with something that's not an integer. But the multiplicative inverse of b is 1 over b. That's a rational number. What exactly is this 1 over b? Well, b is 1 over b, or b inverse, is a solution. Because I don't want to use division to sort of define what I mean by division. So this is a solution to bx equals 1. Right? And x is 1 over b, which is the thing I want to define. We can do the same thing with modular arithmetic. And it turns out that these often will exist in Z mod NZ. So these are sort of more special in the integers in some ways. You actually do get some numbers that you can always divide by in Z mod NZ, even though you cannot divide by them in the integers if you want to stay in the integers. So in general, we say some integer a is invertible. Think like you can write it as a 1 over a. So it's invertible modulo m if, we need to specify a modulus too, if ax is congruent to 1, mod m has a solution. Okay. The solution will always be unique because here, if you think about it, what's our statement? So ax minus mk. Sorry, I'm trying to do two things at once. So what does the definition say? It's ax minus 1 is equal to mk. Ax minus mk is equal to 1. So if GCD of a and m is not 1, then there's just no hope of solving this. So we need the GCD of a and m to be 1. In fact, we'll come back to that in a second. But yeah, if the GCD is 1, it's going to be a unique solution. And we denote this solution. We denote this solution by I'll denote by this symbol. So a to the negative 1. Okay. So we can define a multiplicative inverse of a, which means we can always divide by a. So to divide, in quotes, by a, you multiply by this element a inverse. And this a inverse, let's look at an example. So it's not really a fraction. It's just a normal element of Z mod NZ. So for example, let's look at 2. So a is 2 modulo 7. Modulo 7. And a inverse, well, what is a inverse? It's a solution to, 2x is congruent to 1 modulo 7. And modulo 7 is small enough where I would just try to think through the possibilities in my head. So 2 times what is congruent to 1? 2 times 4 is congruent to 8, which is 1 more than 7. So 2 times 4 is congruent to 1. So here a inverse is just the element 4. See, it behaves like 1/2, but 1/2 is just 4 in Z mod 7Z. Okay. So this element 4 is a multiplicative inverse of 2. You can multiply 2 by 4 and you get 1, which means you can always divide by 2 by multiplying by 4. Let me show you an example of how you'd use this. If we want to solve a congruence, for example, 2x is congruent to 3 modulo 7. Note that 2 is invertible mod 7. Because this has a solution. So we can, how would we solve this equation over the integers? We divide by 2. It actually was 3 halves. We can still solve this modulo 7. Instead of dividing by 2, we multiply by 4. We multiply by the inverse of 2. So we can multiply by 2 inverse, which is just 4 modulo 7. Here's what that looks like. I do 4 times 2x is congruent to 4 times 3. We're always allowed to multiply congruence by anything. We're not always allowed to divide. That's what we're trying to kind of define here. But we have to do it very carefully. But we can always multiply both sides of a congruence by any number. And here we get 8x, but 8x is just x. Right? Because 1 is congruent to 8 mod 7. So we get x is congruent to 12, which is 5 mod 7. So this is a very nice way of solving some linear congruences. You can't always, sometimes this number may not be invertible, but you can still solve the congruence. So what do I mean it may not be invertible? So there's a very specific criterion for if a number is invertible. So an element A, this will be the last thing I'll do. So an element A is invertible mod M if and only if what do we want? So we want to be able to solve this, which means we want a solution to this. Right? Well, if A and M are relatively prime, we can do it, right? Because if A and M, if their GCD is 1, then by Euclid's algorithm, we can write to 1 as a linear combination of A and M. If A and M share any factor whatsoever, we're out of luck, right? Because that factor must also be shared by this 1, which is a contradiction. 1 doesn't have any factors that are in 1. So an element is invertible mod M if and only if the GCD of A and M is 1. If they're coprime, they have no factors in common. Okay? So for example, in Z mod 6Z, there are only 2 invertible elements. 0 is certainly not invertible. 0 is never invertible, just like you can't divide by 0 in the integers. 1 is invertible because 1 and 6 are coprime. 2 is not invertible. It shares a factor of 2. 3 is not invertible. 4 is not invertible. It shares a factor of 2 with the modulus 6. 5 is. But it's only 1 and 5. So only 1 and 5 are invertible. Okay? But in Z mod 7Z, every non-zero element is invertible. Do you see why that is? So every non-zero element is invertible. Well, it's because the condition is you just have to be coprime to the modulus. You have to be relatively prime with the modulus. And everything, 1, 2, 3, 4, 5, 6 is coprime because 7 is prime. It doesn't share any, it can't share any of these factors by definition. Well, it shares a factor of 1, but that's okay. Okay, great. So this is going to be a tool that we're going to use a lot. It's a very powerful tool. For example, if we have a modular inverse, we can solve an equation just like we normally would by multiplying through by the inverse to cancel out this 2. However, we have to be careful because, like for example here, 2x congruent to 4 mod 12, 2 is not invertible mod 12, right? So there's no such thing as a 2 inverse. However, we can still solve this equation. And there are actually 2 solutions. So in general, we have to do this sort of more complicated general method. However, modular inverses are very, very important and useful, and we'll be talking about them quite a bit in the lectures to come. All right, that's about it. Thanks for watching.